mute there. Okay, so hello everyone. Welcome to day 8 of the online course about the DeSIRe code. As always, thanks for joining us today. Today I think is a very interesting class because we are going to perform NLTE inversions with DeSIRe and in
we
parallel.
again have a same problem, Carlos. Now in the
Yeah.
sides, yeah, there are. Oh, now it's gone.
Now it's gone. Now
yes.
if I do this, it appears again.
No, now it's
no.
Yeah.
Okay. If it appears again, just let me know because I will try to do something. Okay. So then we will cover today inversions in NLTE and in parallel. That I think is going to be the main mode that you will use in the future, because even if non-LTEs are inversions with DeSIRe are relatively fast, you will have big maps. It could be with current telescopes or with future telescopes. So I think parallel is going to be the best option for at least trying to get something from one map or several maps. So then the idea is that we will start from the profiles that we synthesized in the previous tutorial. If you remember, they were from the before simulation. And at the end, when we read the profiles, we added noise to them. And then we just saved them in a proper format. So, and then what we are going to do today is embed them starting from a combination of 7 empirical models. I think I'm using different file F and file C. And the idea is that we start from a very, very simple atmosphere, and then the code will try to modify that atmosphere in several iterations until reaching something close to the complex atmosphere that we have here from the before simulation. So then today, because I think from time constraint, I think it's better if we just focus on the inversion process. And in a future class, I will show you how to prepare the different set of initial atmospheres. I will try to do it either in IDL or Python or both. And also I will try to prepare a folder and put it on Dropbox with different semi-empirical models that we have extracted from the literature in the last year. So it could be the DeSIRe atmosphere, the FAL models, the FAL F, P, S, all the models. Also the hot and cool atmospheres from sunspot modeling. So all these models, I will try to put them on a single folder. So then you can take them and create a set of initial atmospheres that not only change on velocity or magnetic field, but also have a different combination of temperature, pressure, electron pressure. So to cover a wider range of physical scenarios. Okay, so then let's test the code. Let's run inversions and check how it goes. One important thing is that as in the previous class, I think that you more or less understand how the Python wrap works from previous tutorials. So I'm just going to cover it just very fast. The idea is that we are going to use almost the same files from the previous class, but just adding some sentences to make it to make inversions. But as always, if you have any question, just ask them now or just send me an email and I will be happy to help. Okay, so then miscellaneous, just one thing. I think most of you will appreciate it. So we created a guide of contents that can be found also in the Dropbox folder. And the idea is that I covered all the tutorials for SER, RH, and DeSIRe, and I tried to put each day what are the main contents. So then if you said, I want to remember how response functions were computed, so then you just go and look for response function and you will see which days covered it or other things. So then this will help you navigate through all the tutorials. So you don't need to go one by one or check in the mail. So just go to that guide of contents and then it will be easy to move and to find what you're looking for. Okay, so then we are going to read this procedure. I will just start and then I will move to the folder where I run the inversion just to give you context. So then let's start here. And also important, if you see that the issues that we had last week are appearing, so there are some flashes or something like that, just let me know and I will try to move around the video for the people. So, but now it's fine. If I do this, you see it correctly, right?
Yeah, as of now, it's on this text editor, it's fine, but on the side of the screen, we see this like some rectangles of blank, gray, white. Yeah, now
Okay.
it's gone. Now it's
Now it's gone. And now it appears. So if I put my mouse over there, so if I do this, is it okay?
Yeah, now it's fine. Yeah.
Okay, so I minimize all the video for the people. So I don't know if it will remain in the final movie, but I think it's better if we don't have these glitches. So okay, so then now it's perfect, right? If I move here, everything's fine.
Yes.
Okay, perfect. So then let's start covering this, and then we will move to the folder where I run the code. So then, as I said, we are going to perform inversions of the data that we synthesize in the day 7. That is iron lines and calcium infrared line. And these are synthetic profiles from the enhanced network simulation that was computed by the Bifrost code. Okay, so we are going to embed that data. And what we are going to use is essentially run almost the same initialization.input file. But now here we are going to provide the profiles. So the location of the profiles, in this case, they are in the same folder. And as I said in the previous class, so you need to have a file per entrance in your wave grid file. So just let me go here. So this is the grid file that we used in the synthesis, and is the same one we are going to use in the inversions. So we have 3 regions. So this is the iron line, this is the calcium 8498, and this is the calcium 8542. So then our initialization input should have also 3 files. Okay, so this is essentially the main difference. And the other difference is that now we have to also define this parameter that you see here also. And the rest will be the same. So it means that we are defining the number of cores. We are going to cover the full field of view. And then this we don't change it because it's the same. And then this is location of the code. So that is the same, except this one. Okay. So now let's cover in detail what we are telling the code there. So then the idea is that the first index is the number of initial atmospheres that we want the code to try to check if the results improve. And the second number, it will be the chi-square value for Stokes I. So in this case, we are telling the code that we are aiming to obtain a 0.99 chi-square. That is very good. And this is related to Stokes I. So then the code, the Python wrap internally will compute the difference between Stokes I, and then from that we'll decide what it will do in the next step. So now I will explain it. But the idea is that this is not the chi-square value that you get from DeSIRe. It's just computed internally by the Python wrap. We are working with Basilio to compute a normal chi-square value additional to the ones that the code to compute. And this will be for the 4 Stokes parameters, so it will be a bit better than this one. And after that, this will be the one that we use as a reference, but it still will be the same. So it should be close to 1, a good fit, and different from those values will be a not so good fit. Okay, so then it will be easy to understand what is a good fit and which values you need to provide in the initialization.input. Okay, so then one example that I ran when I was preparing the class is this one. So I told the code this, and then the code ran. This is only 4 pixels. And then what we got is, it says that in the 4 pixels, it ran the 4 atmospheres. Okay, and it got in none of the cases, it reached 0.99, so it was close, 98, but it never reached 0.99. So for this reason, it covered all the atmospheres that we provided. But then in some cases, the best solution, he obtained it, or the code obtained it with the atmosphere 1, and in other cases, in this example, with atmosphere 4. So then if you tell this the code, then it will try to reach this 0.99, running all the atmospheres that you are provided in the first part. And if none of them allows to reach the threshold that you are providing, then the code will pick the one that obtained the best results. But sometimes could be the first one, or sometimes could be another one. Okay, and this is the time. So it was 5 minutes in this case. So in general, I would say that it's better to, at the beginning, to just simplify things. So then in this case, you have mainly 2 options. So one is to run with only 1 atmosphere. So then you can put here 199. And then in this same example, you have that the code run again. The previous cases where the best result was obtained with atmosphere 1 are the same. And the case where, so this is pixel 00. So pixel 00 that before was 0.9899, now is 0.984. That still is reasonable. So in this case, you are doing the inversion in 1 minute, and you're obtaining essentially the same results. So then my advice is that for first test, don't put this value more than 1, because you don't need it at the beginning. Just give it a try over a given region just to check how the code behaves, and then you can decide to increase this number if you want to have a smooth pattern. I will show you examples later about this. So, but another option is that if you see that you are never reaching the value that you're providing, of course, you can decrease it. So maybe instead of saying 0.99, you can say 0.95. In this case, is the same. So, but in this case, I'm setting 4.95. But as with atmosphere 1, we are always reaching higher than 95. Then it's basically running only just 1 atmosphere and getting the same result as before. So then I think it's fine. So here's this one. So I think it's fine to choose one option or the other. The important thing is, my recommendation is just start with 1 atmosphere, but be certain that you are getting reasonable results with that atmosphere. Because, for example, if we have this same example, same configuration, and instead of running it 4 cycles, that was the configuration that I was using in this case, we run it 1 cycle with only a few nodes in the atmospheric parameters, then it's really fast. Now it's only 20 seconds per pixel, but you see that the chi-square values are now lower, so 93, 95, 96. So then, and with 2 cycles is a bit better, but still is not close to 99. That was the previous case. So then my advice is try to go simple at the beginning with 1 atmosphere, but be certain that the results in terms of the configuration that you are using, the nodes and everything provides reasonable results, because otherwise you need to iterate a bit until you get close to 0.97, 98. Okay. So then now let's start with the program itself, where we are going to check results and study a bit all the tests that I did. Just as a note, when I was preparing this last week, we had IDL issues. So when I was trying to connect and get the license from the servers, there was no option, so I couldn't start IDL. So I said, well, I think this is a good trigger for start practicing Python. So then everything today will be a Python script. So then it's my first of real Python script. So I think it's really bad, but is functional. So just go through it. And if you're an expert on Python, just don't be too harsh on me. But I think it's functional. So this is an important thing. Okay, so then essentially we load some packages, and here I define some things related to the figure because we are going to make I think a bit elaborated figure. And then we start loading the results. So the idea is that we were here, I run the code in this folder, and then inside results, you will see that I made a lot of tests, and we will see them today. But you can run the program. The one that I'm sharing with you in this class is this folder. In fact, it's this compressed file. So then inside you have results, and we are going to read this atmosphere, that is the resulting atmosphere, and we are going to compare it with the initial one. Okay, so then the initial one is this one that is located in the folder that we use in class and the previous class. And then the inferred atmosphere is located in the place where we have this program. Okay, so then we just use this sentence, and then using this command, you can get information of the fits file that we are reading, and we can see that is what we had before. So this is X, Y, and this is optical depth, and this is the 11 physical parameters from optical depth to gas density. And both cases we have the same. So then we can read the data with this option. But then if you print this, that is like help more or less in IDL, it will tell you this. So just be careful, because with IDL we created this format, and now it's changing it a bit in this way. It's rearranging the axis, but also it's flipping it. So in this program, what you will see that I shift also or flip the arrays to have it as intended. So just be careful with that. And then the important thing is that we want to compare the original atmosphere, that is this data original, with that is this data inverted. And the idea is that we want to compare it at the same optical depth. So for example, log tau 0, log tau -2, or log tau -5. But we use an input atmosphere that we got from RH. If you remember, the optical depth was computed from RH, and then we had a given extent in height. But then we started the inversion with a different atmosphere. So the first thing I do here is to print this, and then you will see this message. So it's important that you check that the index that you are using to compare both arrays, they correspond to the same optical depth. Okay, so in the input atmosphere, 15 is log tau 0, and in the one that I use as an initial atmosphere is 12. So just be careful, because if you are comparing the results at different log taus, then definitely you will see that the results are not good. But
Carlos, can you hear me?
Yes.
Yes, but that is because the input atmosphere and the inferred atmosphere, they have different optical depth. And
yes.
Why is that?
Because I use as an input the bifrost atmosphere, and I invert it with a foul atmosphere.
Okay.
Yes.
Thank you.
Yes. So the idea is that I use a very, very complex atmosphere for the synthesis. So
I understand. Yeah, completely understand. Thank you.
Okay.
I missed that part.
Yes. Yeah, no, it's fine. Okay. So then it's just that. So just be sure that that they have the same. So you are comparing the same index. Okay. And in this case, as both were interpolated to delta log tau 0.1, then as we want to compare log tau 0, -2, and -5. So then in the case of the input atmosphere, this is 15, then 35, because the step is 0.1, and 61. So this is log tau 0, -2, and -5. And in the case of the inferred atmosphere, this will be 12, 32, and 62. Okay. So then here is very simple. I just define temperature at log tau 0, 2, and -5. As I said, I needed to flip the arrays to just make it as the one we want. But then I didn't change anything else. And the same for velocity and the longitudinal field. So I think these three parameters are enough for just having an idea of how good the results are. And in this case, I'm also changing to radians the angles, inclination, because it seems that like in ideal, if you want to compute the cosine or sine of a given value, it should be in radians. It will not work in degrees. So just be aware of that if you are a rookie in Python like me. Okay, so then now it's the same. So we are going to save the temperature at log tau 0, -2, and -5, but from the embedded data. And I again here, I emphasize that be sure that the index that you are using here is the same, so correspond to the same optical depth than the one you are using from the input atmosphere. And I think that's all for the reading part. And then just is things that I put to make the plot to look reasonable. So I will just cover it very, very quickly. And now we are going to focus on the results itself. So it's just defining the figure, and we are going to plot. And let me show you the figure, and I think it's easier. So we want to do something like this. Okay, so it's relatively complex figure. So we have input log tau 0, inversion at log tau 0, input log tau -2, inversion log tau -2, and the same for -5. These are different rows. And then columns will be temperature, line of sight velocity, and longitudinal magnetic field. So this is the field strength times the cosine of the inclination. Okay, so then this is essentially all these lines that I happily wrote. And then
So
with
Carlos, what's the reason that for -5 it was not
yeah.
matching? Like, oh.
Yeah, it was bad. Yeah, but I will enter now there. Yeah.
Okay.
Yes, thank you for the question. So then this is just what we are going to do, and this is just to save the figure. So now let's go to the different tests that I made. Okay, so then the first one, and as Nancy pointed out, it was looking not so good at log tau -5. So then let's start with what we did here. So the name, it says 2 cycles, 1 at initial atmosphere, and weights are all 1. Okay, so then this is what I, for example, would recommend you to try the first time that you have any data. You don't know exactly how it will work. So then here the temperature, I think, has like 4 nodes, but then velocity and magnetic field, I think they have linear gradients. So then this means that the results, for example, for temperature are good in general. They are also good here, but then here it's not so good. And in fact, if you check this pattern, and this pattern here is essentially the one that you have here. And this is because you don't have enough nodes to let the code change the temperature certification in upper layers. So essentially it's just extrapolating what we have from lower layers. So results are reasonable, but still limited for such a complex atmosphere. And the same for velocity. So velocity is very nice in log tau 0 and log tau -2. But then here you see this pattern, okay? And then as Nancy was pointing out, this is essentially the same that you have here. And this is because the code is not able to modify it on height with a limited number of nodes. So it's just extrapolating what you had at log tau -2 or -1. And then for this reason, it looks so bad. Okay, so then I would recommend you to start with something simple like this one. But as soon as you see that it looks fine, but it's a bit, it's something is missing. So then, yeah, you can start adding more nodes to the atmospheric parameters. So for example, in this case, you have that 4 cycles. So this is the configuration that I was using. So 2 cycles was until here, okay? And now we are going to add 4 cycles. So we are going to reach this freedom, okay? So then is this one, still 1 initial atmosphere and without playing too much with weights. So then here again, it looks good in lower layers, okay? Temperature looks fine. Now we are seeing a bit more pad points, but I think because it's trying harder to improve this part here, but there's some shadow here from the lower layers. But at least the magnetic field now looks much better. So before it was essentially a trace of what we had here, and now it looks much better. Although now you can see also a lot of salt and pepper or red and blue patches, because the code is trying but not really obtaining a good solution. So then I said at that point, okay, maybe we can improve enhance the weights of the calcium lines, just to tell the code, please pay more attention to the upper layers, because you are not really achieving a good result there. And then I started with the same 4 cycles that I think is good. So we saw an improvement of the magnetic field. Still 1 atmosphere, because I wanted to just check if it works. And then once I completely sure that is what I wanted, then we can add more atmospheres. But then I put 10 times more weight in the core region of the calcium lines, as we did in class 6, that we saw that it was an improvement. And at that time, the photospheric lines, they were still relatively good. Okay, so then what we have here is that it seems that we went too far, because here it doesn't look so good, and temperature now looks very bad here. But here it seems that at least we don't have the pattern that we had in middle layers. So it's trying, but also velocity, it's missing the velocity in lower layers. At least it's not as good as before. And here I would say that it's better, because this red concentration here, now it's here, this thing here is starting to appear here. And also this looks nice in the sense that, well, it's still not clean, but this is also looking good. But I think it's probably too much, because we are also missing the clean certification that we had before in lower layers. So then I went down to 5, and then things here start to improve. So then we have here more red and more blue, but still we are having a lot of complex patches here. So then I said, well, let's move to 2. So now we are still with the same configuration of 4 cycles, but the weights are only 2 times larger for the calcium lines. So then now it's not as good as before, but I think here it's starting to, so these hot patches are, I think they are well recovered, and velocity, it's also reasonable. And here I think this is okay. And finally, the magnetic field, I think it looks nice. So you see this shadow here, this red one, there's something here. So at this point I was saying, okay, I think that's starting to look reasonable. But as I did something similar in the paper, I was a bit concerned of if I was choosing the atmospheres that I wanted to have. So then I went to the folder where I ran the inversions of the paper, and I copied that atmosphere, because in this case it's only file C. But from the paper, I remember that it was a file F, file C, and HSRA. So the atmospheres, they have different temperatures. And then I give it a try again. So then this one is, again, 4 cycles, 1 atmosphere, 2 times more weight in calcium, but with a different initial atmosphere. And then I think it's a bit better. So temperature looks smoother. It looks good here. And then here it looks better because now you see more dark patches corresponding to the cool regions that you had before. And I think the hot regions are also reasonably well recovered. And velocity, I think, looks nice. So then just let me go back 1 second. Below lower layers looks fine. And then here it looks a bit better. So you see, as I said before, this red thing is starting to be here, then this red here, then this red patch here, and then here. So I think it's better. And this one, it looks cleaner than the other. So I think this atmosphere is probably another file model. And I said, okay, that's a bit better. And also this one goes up to minus 6.8 optical depth, while the initial ones, they reach like -7. So maybe just going a bit lower in the atmosphere, it's better. So then I said, now let's run this final test with 5 different atmospheres that I had from the paper to check if things improve. And in this case, I will just bring the 2 folders, sorry, 2 plots. It's like this, and then I will make it bigger. And then I will open the previous one. Yes. So in this case, what we are comparing now is the impact or the possible impact of adding different initial atmospheres. Okay. So then let's start with temperature. Yes. So in this case, you see that the black dots that they were here when we use 1 atmosphere, now they are not here. So it looks a bit smoother. If we go up, let me pick bigger, and then this one also bigger. So you see the same pattern. So here we had black dots that are probably or not good solution of the code, or simply that the result was not good. But now it almost all of them disappear except maybe one here. And then in upper layers, things are reasonably the same, but because it's very complex, but still in both cases, we have a larger contrast than what we have before. So we have dark areas, we have hot areas. Then let's go to velocity. So this is velocity at log-tau 0, and this is velocity at log-tau 0. So you can see that it's essentially the same pattern, but you had more white dots, for example, in the intergranular lanes that now are less present here. So I think it's a bit better. And the same for the velocity at log-tau -2. So it's not changing drastically, but it's being, let's say, more consistent. So having different atmosphere with the small variations in velocity or sometimes in temperature, it will allow the code to obtain solutions that are better, and it will translate on maps that are simply smoother. And this is because of the inversions are a bit better. And I think here you can also see it. So here I think you had more like salt and pepper, and here is smoother. And then finally, let's compare to magnetic field. Just 1 second. And here, okay. So again, here, let's go even to deeper detail. So you can see that the patch that should be a uniform magnetic field, here we had some white dots, a few of them normally, but now they are almost disappeared. So again, the code is being more consistent without any external information. So I mean, we are not telling the code your neighbor pixel has a magnetic field that has given polarity, so maybe try to match it. So we are not telling anything in the code, so just pixel by pixel inversion. But as we are offering the code to move around in the chi-square domain, is essentially getting better fits that better match the initial atmosphere and make it smoother. So now go down and we have the same. So here are some white patches where it should be like a uniform and unipolar network patch. So here is a bit smoother. And then down, again, it's almost the same, but maybe a bit cleaner. So no these red dots here, maybe some still remain. So I think this is probably a very good configuration. And then before comparing with the atmosphere, because I was just comparing between different inversion configuration. So before that, what I did, I will go very, very slow. So I started with 2 cycles that, and they will have less freedom. So 5 nodes in temperature, and then just a few nodes in other parameters. I saw that it was working well. I said, okay, now I'm going to jump to 4 cycles. And in all the cases, I was not adding additional atmospheres or weights. So everything, and I had weights between the stock profiles, but wave-independent weights, they were always 1. So with 4 cycles, I said, okay, it's improving, but still I see that upper layers are not well recovered. So maybe I can play a bit with weights. So I went to 10 and it was too much. Then I went to 5 and still too much. And I went to 2 and I said, okay, now we are getting good results, but still I felt that the atmosphere that I was using was not the best. And I knew that maybe starting with a different atmosphere can help. So I tried, and this is this one. And then I was happy with this one. So I said, now let's try 5 different atmospheres that are essentially a combination of this one, plus maybe another semi-empirical model that has a slightly different temperature. So for example, HSRA, FAL, they are slightly different. So I tried, and then we got this final solution that for me, I think I'm really happy with it. So did you follow the process? Any questions before I compare the input with the inversion? No? Okay, so then what we have? So I think we have very good results. So the photosphere, so the low photosphere lockdown 0, it's very nice. I'm really happy with this. Middle layers, I think here the iron lines are really helping a lot because they are very sensitive to this region, and we have 2 of them. So then we are recovering temperature excellently. I think with the calcium line, maybe we can get something, but then velocities and magnetic field is probably just because of the photospheric lines. So they are very good. And then things always become much more complicated when we go to upper layers. But I think still the code and the lines and all the combinations are working well because we are recovering a lot of things. But it's true that we are failing, for example, here, all these dark areas that are very, very cool chromosphere. We are not able to reach them. I don't know if this is a problem of the code or something, because there are several factors like the type of lines that we select, the noise that we added, the complexity of the atmosphere. So if you see this, for me, I'm happy, but it's true that we are not having as high accuracy in upper layers than in lower layers, but it's still very good. And also it's important to note that sometimes like this, so this is all red, but then this side is deciding to put here blue. And in this case, I think essentially is that for any reason, the lines are not so sensitive there. And the code is just saying, okay, blue seems to work, or maybe it's extrapolating from lower layers. But it's true that sometimes we are not even matching the sign of the velocity. But again, I think this is because it's really up in the atmosphere. So I'm not sure who is the most important factor, if it's sensitivity, if it's the configuration that we are using, or other things. And then here, for me, I'm really, really happy here because this is, so you see this nice red color, this is 100 Gauss. So this is essentially close to the noise that we were putting. And also these blue things, this is between 200 and 300 Gauss. So being able to reproduce at least the shape of these very weak magnetic fields, I think is excellent. So in fact, you can see if you go really, really deep, this small red thing here there's a shadow here. It's not as good as you see here because it's really nice, but we are overcoming noise and still there's something there. So I think this is really, really, really good. So if you have something like this, when you are doing test, then just stop here because I think it's you obtain it a really good configuration. Okay, so then I think this is the main part related to that, and I will enter in the summary now. Is there any question before that?
Carlos, can you
Yeah.
please remind me what is the spectral resolution of your data or the spectral sampling?
Yes, so it's in this case we are using 10 milliangstrom for the iron lines and 20 milliangstrom for the calcium lines.
Okay, thank you.
Yeah. And as a reference, the initial atmosphere, I think it was 90 points in optical depth, and we are having 9 nodes in temperature and a maximum of 6 in velocity or magnetic field. So we have a very complex atmosphere that is changing with height, and we have nodes that are located but in a very wide range. So the code is able to do some things, but it's not going to be able to really have the very short, small scale variations that you have in a simulation or in the sun.
Can I just say one? Be careful. This is the code basically have infinite spectral resolution, right? Because we are doing a forward calculation. So we have spectral sampling at the measure that you indicated, but we don't have, that's not the resolution. Just be careful with those terms because they're different.
Yes.
Yes, of course. But at the end of when you synthesize, then you apply a spectral PSF or whatever and select the points that is in
correct. Yes, and then you have a spectral resolution. But yes.
Okay. Yeah. Thank you. Thank you for the clarification.
Okay.
Thank you.
Okay. So more questions? No. Okay. So then, as a summary, we embedded. Well, I embedded the map a lot of times. And the time is, so this is 230 times 230 pixels. I was using 100 threads, and the time is 12 hours for the 2-cycle case. Then 17 hours for the 4 cycles. So here you see a jump, but it's only 1 atmosphere. And then a jump here up to 21 hours when I put it the 5 initial atmospheres. And the reason why it's not 5 times is because I carefully checked that the first atmosphere was in general the one that was working well. So for example, this is just a print of what you see when the code was running. This case was when it was running around 66% of the map. And you see that there's a lot of 0.99 results. That it means that it's very, very good, at least the Stokes inversion. And it was run with 1 atmosphere, and then it was, of course, picking 1 atmosphere. Then you see some pixels that they take longer. So this one, it was run 5 atmospheres, and the one that provided the best atmosphere was 5. It was good because it was very good fit. But of course, in this case, it was 800 seconds compared to sometimes 200 seconds. But the idea is that in general, the most common case was 1 atmosphere. And only for a few pixels, it needed to run 3 or sometimes 5. Okay, so then it's important that you try to do some tests and try to optimize your run in that sense. So if you see, you pick a small patch, like, I don't know, 100 times 100 pixels, you run the inversion, and you see that the atmosphere that in general is providing better results is number 5. So then in that case, just rename number 5 as number 1. So then the code will always try that atmosphere first. And then if that atmosphere doesn't work, it will move to another one. So in that sense, you are not multiplying by 5 the time that you are getting, you are multiplying it by 1.5 or sometimes even 2, but you are getting better results. So the idea is that try to put an atmosphere that works well as a number 1, and then different possible combinations in a higher order number, like 2, 3, or 4. So then if some pixel is complex for any reason, then the code will try that pixel with different atmosphere. But if a pixel is okay and can be well fitted starting with atmosphere 1, then it will go very fast. Okay. But just as a note, you see here how many days I was inverting the map, because I was trying to have it as good as in the paper, but with noise and with different configurations. And I think the code is working well. And of course, you need some trial and error, but as soon as you get it, for example, in this case, I was happy with this one. So then if you have a time series, then I will just embed the time series with only that configuration. So it's only pick a map, you pick a representative region, play a bit with that, and then you have the configuration for all the maps or the time series that you have. Okay, I think this is all that I commented before, so the results are good, and not in all the cases we have very good. Sorry, is this one? No, this is just the result. This one. But so sometimes, mainly in the upper layers, we are not getting, let's say, perfect results, but these could be maybe the configuration we're using, the selection of spectral lines. Maybe we are not reaching as high as we think, or depending on the physical scenario. We also have noise. So then if you have very weak polarization signals and you have noise on top of that, then you cannot really do too much. And also that the simulation is very complex, and we know that they have some limitations, so we should not really worry too much about that. So I think there are a lot of contributors, and I think all of them contribute somehow, sometimes a bit more, sometimes a bit less. So it's not only one cause. But in general, I'm really happy with them. And always try to think also that we are using as an input a very complex atmosphere with, let's say, high optical depth resolution, and we are embedding with 9 nodes and with a given selection of lines that they have their response function that is not completely uniform in all the range. So you have variations, and the code it has some limitations that are intrinsic of inversion codes, but still it's working very well. So then I think with that, with an example of how I would run a given inversion multiple times, playing with different configurations and things like that, I think you're ready for doing inversions. Okay, so then I will go back to the presentation again. I don't know if I'm going a bit fast today because I move around a lot, but could you follow everything, or is there any question? No? Okay, so then I will go back to the presentation, but what I'm going, so this is what you have already in the Dropbox folder. So this file contains, so we are in results. So I made a compressed file of this. So what you have inside when you are going to run it is, this is the output of the code and also the figures that I create with the Python wrap. And then inside you have a copy of the configuration files that I use. So the exactly ones. And so then the idea is that if you want to run the code, you need to copy all these files in your main folder, and because inside is where you have all the keyboard, the wave read, and things like that. So what I do is I run the inversions here. So you see that you have run files and then a few files. Okay, so I always copy these ones. So then if you want to run it, just create a file, a folder, let's say Bifrost inversions, and then inside that folder you need to copy what you have inside config. Okay, So this is the initialization.input. This is the Python wrap, and these are the run files that I use. Okay. And this is with, here you have the grid file, the weight files, the keyboard.input, the control files, and then the atmospheres that I use, and the input files like abundance or the atom and things like that. Okay. I didn't copy all the all the text because, as you can see, each text is like 3 gigabytes, so I didn't want to fill the Dropbox folder with just text. But if you want, just give it a try or just let me know. Okay, so then let's go back to the presentation, and here we are. Is it now working? Do you see any issue or no? Okay. So I will assume that it's working.
It's working, yeah.
Okay,
Yes.
thank you, thank you. So then, as I said, try to examine the files that we covered today. For me, it's important to, if you try to think of, I'm changing the configuration file, then I go to the initialization.input, I run it, I'm selecting a given threshold with initial atmospheres. So try to go step by step through the process. I think it's complex, but just go step by step. And I think it's important for me. I think the important thing is don't try to get perfect fits the first time that you get data, because if it's from an instrument, you probably have some issue with the wavelength calibration or with the termination of lines, something like that. So don't spend 5 days waiting for the first run to be done because maybe you had a technical issue. So the best thing is just run with something simple, a few nodes, one initial atmosphere, check if there's an issue. If the code struggles to get fits, then maybe there's a calibration problem, or of course you may need more freedom. But usually if you have like 3 nodes for temperature, you should get the continuum right, and probably the line core of photospheric lines, you should get it most of the time. So try to always go step by step before trying weights and other things, okay? And then very important, so I knew that it will take a lot of time to compare atmosphere and to explain the process, but we also need to check profiles. So we haven't seen any profile today. I put it on Dropbox so you can compare them, but it's important that now we are comparing atmospheres because we have the input, but when you have observations, in general, you don't have any input. So you have to, my advice is get inversion done with a simple configuration, check if the granulation looks like a granulation, if the temperature looks okay, the velocity looks okay. And then as soon as you have something that looks fine, every time that you try something different, it could be weights, it could be more nodes in a given parameter, check the atmosphere, but also check the profiles, because the profiles are the key. So if you have an atmosphere that looks smoother, for example, than the one that you had before, but then when checking the profiles, you are not fitting well, I don't know, some lines, then something is missing. So then always don't forget to check the profiles. And my advice is, if you are, for example, in this case, that you have 231 times 231 pixels, you don't need to go one by one. So just take, for example, 1 pixel in the network patch, 1 pixel in a very quiet area, 1 pixel in the edges of the network patch, because there the magnetic field is inclined and complex. So take like 5 pixels, and then every time you change something in the configuration, check what happens with those pixels, with atmosphere in general, but also with a few pixels, because this will give you some confidence and some, let's say, leverage to say, I thought this is my best configuration, and this is because the atmosphere looks fine, but also because the fits are good. And then you can be more confident that you are going in the right direction. Okay. So then next class, we will continue with a lot of exciting things. I want to cover several things. So one is to get data, imaging data from, for example, from SST-CRISP. We did something in the DeSIRe class, but I want to do it again. And in this case, we'll be combining an observation of 2 lines. So for example, iron plus calcium 2, 8542. So then this will require preparing the data sets separately, but also providing some special files that we haven't touched yet, like PSF, the spectral PSF. It's going to be different from the 2 lines because they are observed with a different filter, a different configuration of Zetalon. So then we have prepared the code to accept any amount of PSF combinations based on the number of entrants that you have in your grid file. So I would like to give you an example. So then in the future, anytime that you have filter graph observations tuning different wavelengths, it should work. Then I want to explain and also understand myself how the chi-square is computed in DeSIRe and DeSIRe. So I will sit down with Basilio, we will write down the equations, I will prepare a program where you said, this is my profile, and this is my configuration file of inversion with nodes and things like that. You run it, and then you get the same value that you obtain with DeSIRe after running an inversion. Also, I will prepare a library with a selection of atmospheres. It will be several atmospheres that I will start from. I will run a Python or IDL program, reading them, modify them, and saving them. And the idea is that you can then adapt it to your needs and change things that you want to change. Also, I want to do the same as in the first point, but related to spectrograph data, because it's different and some things need to be done slightly different, but it's not so big. And I hope it will be, so now I'm doing it with PTT data, so maybe we can use that as an example, but hopefully we will be able to do it with decreased Visp data at some point. But the truth is that, as you can see, those contents will not fit in one class. So the idea is that I'm confident that you have been following and you have all the information available to at least try to do inversions. And I need a break. This is, I think, we have been 1 year and almost half. So it's been a long tutorial. And I need to rest a bit. So then the idea is that definitely we will cover those topics, but it will not be in 2 weeks. But I can promise that this is I consider it as a living course, because I'm also learning on the process. So then my aim is that eventually, maybe in 1 month or 1 month and a half, I will send you an email to everyone on the list. Hey, I'm going to give another class. It will be that date. If you are interested, just join us or just check the YouTube recording after that, and it will be focused on that. And if someone is working with me and we are finding something that we believe it could be helpful for everyone in the community, then we just prepare a class and then we make it available for everyone. So then you will see me a lot in the future. Don't worry. I like to talk, even if my voice is not as good. But I think I cannot continue having every 2 weeks class, because it takes a lot of time, and I need to work on other things, mainly now in summer. So then we will work together, and so just stay tuned, and we will see each other soon. So then before wishing you good luck and a nice weekend, is there any question that you have from today's class, or any question in general? No? Okay, so then enjoy the weekend, and I hope to see you soon. Okay. Okay. Bye. So just let me stop recording.